I want to tell you about a telescope that doesn't exist yet. Its mirror hasn't been ground. Its instruments haven't reached final design. The engineers who will assemble it are still being organized, and the launch vehicle that will carry it hasn't been chosen. By current schedules, it won't reach orbit until the early 2042. Most of the people working on it today will be near the end of their careers by the time it produces its first image. And yet, this telescope, which exists right now only as a set of requirements and a shared institutional intention, may be the most important scientific instrument humans will build in the 21st century, because it is being designed to answer a single question that no telescope has ever been capable of answering before. Is there life on another world? Not could there be, not is it plausible, not what would we look for if we ever got the chance. The Habitable Worlds Observatory, if it works the way its designers intend, will produce direct evidence that answers the question yes or no on specific planets, around specific stars, within our lifetime. I've spent the last two videos walking you through the space telescopes we already have and the one that launches next year. Hubble, Webb, and Roman together represent the current state of the art. They are extraordinary, but none of them was built to answer the question we actually most want answered. That question requires a different kind of machine, built to different specifications, aimed at a different problem. That machine is the Habitable Worlds Observatory, and the story of why it exists, what it will do, and why it matters is the story I want to tell you today. If you stay with me, I'll explain exactly what finding life means for a space telescope, why it's so much harder than it sounds, and what the specific technical breakthroughs are that will make it possible for the first time in human history. And at the end, I'll tell you the honest truth about what happens if it succeeds and what happens if it doesn't. For most of human history, the question of whether we are alone in the universe was a philosophical one. There was no way to answer it. You could argue from probability, from theology, from imagination, but you could not gather evidence. The question was, in a strict sense, outside the reach of science. That changed in 1995. That year, astronomers detected the first confirmed exoplanet orbiting a sun-like star, a gas giant called 51 Pegasi b, whipping around its star every 4 days at absurdly close range. It was nothing like Earth, but it was the proof of concept that changed everything. Planets exist around other stars. They are detectable, they are numerous, and if we could detect one, we could eventually detect others. In the 30 years since, we have found approximately 5,800 confirmed exoplanets. The catalog grows every month. And within that catalog, a small but growing number of worlds appear to be roughly Earth-sized, in the habitable zones of their stars, meaning at distances where liquid water could theoretically exist on their surfaces. These worlds are the candidates. They are the addresses we would visit, if we could. But here's the problem, and this is the problem that has organized an entire generation of astronomical planning. We can detect these worlds. We can measure their orbits, estimate their masses, and in a few cases characterize their basic properties. What we cannot do with any telescope currently operating or currently planned before HWO is see them directly. We cannot photograph them. We cannot analyze their atmospheres in the detail required to determine whether they harbor life. Almost every exoplanet we know about has been discovered through indirect methods. The transit method watches for tiny dips in a star's brightness when a planet passes in front of it. The radial velocity method measures the tiny wobble a planet's gravity induces in its host star. These methods work brilliantly for detection. They tell us worlds exist. What they cannot do is show us those worlds directly, because the worlds themselves are lost in the overwhelming glare of their host stars. Imagine standing in Los Angeles at night and trying to see a firefly hovering next to a lighthouse in New York. The firefly is emitting light, but the lighthouse next to it is emitting roughly 10 billion times more light. From your position in Los Angeles, you cannot separate the firefly's photons from the lighthouse's photons. The firefly is there. It is real. But it is invisible to you not because you lack the resolution to see it, but because the contrast between it and the object next to it is beyond what any instrument can distinguish. This is the exoplanet imaging problem. An Earth-like planet next to a Sun-like star reflects roughly 1/10 billionth of the star's brightness. Detecting that planet directly requires a telescope that can suppress the star's light by a factor of 10 billion while preserving the planet's light. This is called high-contrast imaging, and until very recently it was considered technically impossible for Earth-sized targets. The Habitable Worlds Observatory is being built specifically to make it possible. Let me lay out what we currently know about the telescope, because a lot of coverage treats HWO as a vague future concept rather than a concrete engineering project. The Habitable Worlds Observatory was formally endorsed by NASA in 2021 as the highest priority large space telescope project. It emerged from the Astro 2020 Decadal Survey, which is the process by which the American astronomical community sets its priorities for the next decade of major projects. HWA won that competition. Its concept was rated above every other proposed large observatory. The current design specifications are still being refined, but the outlines are clear. HWA will have a mirror somewhere between 6 and 8 meters in diameter, comparable to, or slightly larger than, Webb's 6.5-meter mirror. It will operate primarily in ultraviolet, visible, and near-infrared wavelengths. It will orbit at the second Lagrange point, roughly 1 million miles from Earth, where Webb operates now. And, critically, it will be serviceable. Unlike Webb, HWO is being designed from the beginning to allow robotic servicing missions to replace instruments, refuel fuel tanks, and extend its operational life. The single most important thing about HWO, though, is not its mirror, or its wavelengths, or its orbit. It is the instrument suite designed to solve the high-contrast imaging problem. HWO will carry a coronagraph capable of suppressing starlight by a factor of 10 billion. This is 1,000 times better than the coronagraph flying on Roman next year, which itself is the most advanced coronagraph ever placed in space. Roman's coronagraph will demonstrate the technology at contrast levels of roughly 10 million to 1. HWAO's coronagraph will close the last 3 orders of magnitude. That 1,000-fold improvement is the entire ballgame. It is the difference between imaging a Jupiter and imaging an Earth. Achieving this requires engineering that has never been demonstrated in space. The mirror must be shaped to nanometer precision and held stable at that precision across observation periods lasting hours or days. The telescope's structural vibrations must be damped to levels below what any current space observatory achieves. The instruments must correct for residual imperfections in real time using deformable mirrors and complex wavefront sensing. Every component must work together at levels of precision that exceed the current state of the art. This is why the telescope will take 20 years to build, not because engineers are slow, because the physical precision required is at the edge of what is technologically possible, and closing the gap between what is currently possible and what HWO requires is going to take a full generation. Before I explain how HWO actually searches for life, I want to place it in the landscape of the telescopes I covered in the previous 2 videos. Because HWO does not appear from nowhere. It is the specific culmination of what Hubble, Webb, and Roman have been building toward. Hubble cannot do this work. Its mirror is too small, its coronagraph is non-existent, and its wavelengths are wrong for the specific molecular signatures HWAO will target. Hubble was not built for this. Webb cannot do this work either, despite what a lot of coverage implies. Webb has produced spectroscopic characterization of exoplanet atmospheres, and those results have been genuinely revolutionary. But the planets Webb can characterize this way are large gas giants, or, at best, warm sub-Neptunes. Webb cannot directly image an Earth analog around a Sun-like star. Its coronagraph is not sensitive enough, and its wavelengths are not optimized for the reflected light imaging that Earth analogs require. Webb has expanded exoplanet science enormously, but the specific question of life is beyond its capabilities. Roman moves closer. Its coronagraph, launching next year, will demonstrate the direct imaging of large exoplanets and prove that the fundamental physics works in space. It will not image Earth analogs, but it will produce the technology validation that HWO's designers will use. HWA is what comes after all of this. Every servicing lesson from Hubble, every infrared spectroscopy technique from Webb, every coronagraph advancement from Roman, all of it flows into HWAO. When HWAO launches in the 2040s, it will be the beneficiary of 6 decades of continuous space telescope innovation. Are we alone? Once HWAO is built, launched, and commissioned, how does it actually go about finding life? The strategy has 3 stages, and understanding them clarifies why HWAO's specific capabilities matter. Stage 1 is target selection. HWO will not scan the sky randomly. It will observe a carefully curated list of roughly 25 to 100 nearby Sun-like stars, chosen because they are close enough to Earth that HWAO can resolve their habitable zones. Stage 2 is detection and characterization. For each target star, HWO will spend hours to days integrating photons, using its coronagraph to suppress the star's light and reveal any planets in the habitable zone. Where a planet is present, HWL will produce a direct image of it. The image itself will be tiny, a single pixel or a small handful of pixels, containing photons that traveled tens of light years to reach us. It will not look like a science fiction planet. It will look like a faint dot next to a suppressed star. Stage 3 is the part that answers the question. Once HWO has detected a planet, it will perform spectroscopy on the light reflected from that planet. Spectroscopy splits light into its component wavelengths and reveals which specific wavelengths are absorbed by molecules in the planet's atmosphere. Every molecule has a unique spectral fingerprint. Water vapor absorbs light at specific wavelengths. Oxygen absorbs at others, methane at others, carbon dioxide, ozone, nitrous oxide, and dozens of other molecules each leave distinctive signatures in the reflected light. If HWO detects certain combinations of molecules in an Earth analog's atmosphere, particularly the simultaneous presence of oxygen and methane, or oxygen and reduced compounds that shouldn't coexist chemically, that would be a biosignature. I need to be honest about how hard this actually is, because a lot of coverage skips the hard part. Detecting oxygen in an exoplanet's atmosphere would not by itself prove that life exists there. Oxygen can be produced by non-biological processes. This is where the combination part becomes essential. Oxygen alone is ambiguous. Oxygen with methane is much less ambiguous because methane and oxygen react with each other quickly in an atmosphere. If both are present in significant quantities, something must be replenishing them continuously. Even so, it will not be definitive. The scientific community has been thinking about false positive biosignatures for decades, and the list of ways nature can fake a biological signal is longer than most people realize. Volcanic activity, unusual stellar radiation, exotic photochemistry. The community is preparing itself for a very long, very careful debate about any positive detection HWO produces. The moment of discovery, if it comes, will not be a clean yes. It will be a decade of narrowing possibilities until the biological explanation becomes the only one left standing. But here is what makes HWAO transformative, regardless of how any single detection goes. Before HWAO, we have no data. We have 0 direct atmospheric measurements of Earth analog exoplanets. After HWA, we will have measurements of dozens. That means many of the scientists and engineers who will build HWO are, right now, undergraduate students. Some of them are still in high school. The astronomers who will actually use HWO to search for biosignatures, in some cases, have not yet been born. This is what makes HWAO different from most science projects. It is not something one team can complete. It is an institutional commitment that has to survive changes of political administration, changes of NASA leadership, budget cycles, technology shifts, and the natural turnover of scientific careers. The astronomical community has essentially committed to spending the next 20 years building a telescope that most of its senior members will be retired by the time it launches. They have done this because they believe the question is worth it. And they are right. Imagine the moment It is sometime in the mid-2040s. HWO has been operating for a year or two. It has surveyed several dozen target stars. Then, one day, a research team announces that they've detected a combination of molecules that cannot be explained by non-biological processes. The announcement would not immediately change anyone's daily life. The planet would still be unreachable. We would not receive messages from it, not because there is no one to send them, but because the biosignature only tells us there is chemistry consistent with life. But something would change, something enormous. For the first time in the history of our species, we would know that we are not alone, not believe, not suspect. No, with the same kind of scientific confidence that we know the age of the universe. And we would look at the night sky differently. Every person who has ever lived has looked up at those stars without knowing whether any of them shelter life. Every human, from the first ones who painted cave walls to the ones watching this video today, has faced that same not knowing. HWA would end it. Whatever the answer turns out to be, we would finally know. That is what this telescope is for. I promised at the start I would tell you the honest truth about the failure case, and I want to keep that promise. HWO might not find biosignatures. If that happens, HWA will not be a failure. A null result would still be one of the most scientifically valuable outcomes possible. Knowing that dozens of Earth analogs do not show biosignatures would fundamentally reshape our understanding of life's rarity in the universe. But I won't pretend a null result would feel the same as a positive one. Culturally, emotionally, in the shape of the story we tell about ourselves, a null result would land differently. It would not be the announcement humans have been imagining for centuries. I think it's important to be honest about this because a lot of coverage frames HWO as guaranteed to answer the question definitively. It isn't. The answer might be yes. The answer might be no. All three are real possibilities, and all three are worth the investment. We have been asking whether we are alone for the entire duration of human civilization. Our generation is the first in history that has both the technical capability to build a tool that could answer it and the collective wealth to actually build that tool. The choice to build it is the choice to take the question seriously enough to actually try. The astronomical community has already made its choice. They are committing careers, institutions, and generational effort to the project. Whether it succeeds or fails, they have chosen to try. None of us chose to be born into this moment, but we are here for it. We get to watch the first serious search for life in the universe unfold in real time. We get to be the generation that lives through the answer.